Uh, Philip is a professor of mathematical psychology at the School of Psychological Sciences of the University of Melbourne. The research interest in his vision and attention lab is to explain how attention and memory mechanisms work with the visual system using the lens of mathematical cognitive modeling. I think we have all read the important articles of Philip, but one of his articles that excites me every time I read his introduction of modeling for continuous decisions. I mean a circular diffusion model. Today, he wants to talk more about modeling continuous outcome decisions with diffusion processes in high dimensions. Yeah, okay, Philip, thank you again for accepting the invitation. So please go ahead.
Thank you, Jamal, for that warm welcome, and thank you everyone for the invitation. It looks like a really great program you have, and I hope you all come away from these 6 days feeling excited and enthusiastic. I hope you can cope with my Australian English accent, the weird local characteristics of this side of the world, kangaroos, wombats, and Australian accents. So what I want to talk about today is diffusion models for continuous outcome decisions in 2 and higher dimensions. So I plan to touch on 2, 3, and 4-dimensional processes, and I will obviously talk about why you might want to consider higher dimensions. And I'll show in particular that the same mathematics that work for 2-dimensional processes also carry over straightforwardly to higher dimensions. But a bit of context first. Let me step back. So diffusion process models are one member of a general class of sequential sampling models of decision-making, or evidence accumulation models, as some people would prefer to call them. So the first order of business, the first question is, why are they interesting psychologically? Why do they have a claim on your attention? What are they seeking to explain? Well, there are various answers to this, but to me, they're interesting because they solve a very basic theoretical problem, which the great applied mathematician John von Neumann in 1956 called the synthesis of reliable organisms from unreliable components. So the unreliable components he had in mind were, of course, the neurons in populations that encode cognitive representations. When we do cognitive experiments, psychophysical experiments, the basic fact that we run up against is that cognitive representations of stimuli are noisy or probabilistic or variable. Now, the fact that the human cognitive system was probabilistic or variable was recognized 100 years before von Neumann by Fechner in 1860, who confronted the problem of variability in his study of decision-making in relation to his work on the just noticeable difference. And he interpreted that variability in terms of Gauss's theory of errors, which predicted that cognitive representations would be normally distributed. And that follows from the idea that if your measurement is made up of a number of independent components, each subject to error, then the distribution of the whole will be normally distributed. And that idea carried over into the 20th century, into Thurston's law of comparative judgment and signal detection theory. The common insight under all of these theories was the idea that the brain's solution to the reliability problem is the same as the statistician's solution. You increase reliability by aggregation. In statistics, you take multiple samples from a population and you average them. And the same argument applies neurally. You increase reliability by recruiting more neurons into your cognitive representation. But if you think that noise or variability reflects the properties of neurons that encode stimuli, then you'd expect that noise to act from moment to moment, as well as from trial to trial, from decision to decision. And the basic premise of the sequential sampling models is that the brain solves the reliability problem in time in the same way as it solves it in space, by aggregation or integration. In other words, it takes successive samples of noisy evidence and accumulates them until there is enough evidence for a reliable decision. Now, the 1960s and the 1970s were a time of significant theoretical development in this area, with numerous contributors, including Stone, LaBerge, Audley and Pike, Edwards, Donald Lamming, Steve Lincoln, Richard Heath, Doug Vickers, and of course, Roger Ratcliffe. And despite the diversity of these various contributions, they were all linked to, or common theoretical antecedent was Abraham Wald's sequential statistics in the 1940s. Now, at the time people first began to develop these models, the idea of noise, of neural noise or cognitive noise, was unobserved. It was Hubel and Wiesel, of course, but basically it was a construct that was invoked, a hypothetical construct, to explain why people are variable. And the technology to record neural activity in awake behaving animals only matured a little bit later. So these are some classic data from Reutemann and Shadlin of monkeys making eye movement decisions in the random dot motion task much beloved of neuroscientists. So the task, as you probably know, involves presenting a cloud of randomly moving dots, some proportion of which move coherently, and the monkey's task was to make a saccadic eye movement to the right or left, indicating the decision about the direction of coherent motion. And all I want to talk to or point to here is that if you look at the histograms of firing rates of activity in neurons in lateral interparietal area, which is one of the structures that is involved in this task, they're noisy in exactly the way you would expect of a probabilistic or a noisy process. And a critical linking proposition was made by Haynes and Schall in 1996, who noted that responses were made when the firing rates reached a threshold or a criterion level, exactly as sequential sampling models assume. Now, there are lots of these models. There are lots of sequential sampling models. This shows a partial taxonomy of them. I'm not going to go through this in detail. I just want to comment that they differ both in terms of architecture and in the process used to model evidence accumulation. So by architecture, I mean whether evidence is accumulated as a single total or separately for every response. By process, I mean whether it's accumulated in discrete chunks or continuously distributed amounts, and whether it accumulates in discrete time, that is, the process ticks like a clock, or continuously. So of these various proposals, arguably the most successful has been Roger Ratcliffe's diffusion model, which represents evidence accumulation by a Wiener diffusion process between boundaries which represent criteria for the two responses. So at the beginning of the trial, noisy evidence begins to accumulate and until it hits either an upper or a lower boundary. The first boundary hit determines the response, and the hitting time determines the decision time component of the response. So diffusion processes in general are continuous time, continuous state Markov processes. The Wiener or Brownian motion process is the unique member of that class, which is also an independent increments process. That is, the increment to the process in any small interval of time is independent of the increments in all preceding intervals of time. Now, the current model, the current successful model, has multiple sources of noise or variability in it. In addition to the moment-to-moment diffusion noise, which allows the model to predict the shape of response time distributions, there are also various sources of a cross-trial noise or trial-to-trial noise, which allow the model to predict the ordering of correct responses and error responses. So the critical sources of variability are in drift rate, which determines the rate of evidence accumulation, and in starting point, which determines where the process begins. And the success of the diffusion model is largely because it does such an excellent job of predicting the shapes of the response time distributions that you find experimentally. By and large, the distributions it predicts are exactly those that you find empirically, and they're the only distributions that it predicts. So it makes distinctive and unique and accurate predictions about distributions. One of Ratcliffe's significant contributions has been to focus the attention of the field as a whole on the shape of response time distributions and to emphasize that they contain a lot more information than is contained in mean response times alone. Now, the last few decades has seen an increase in the use of a very different kind of decision-making task, of continuous outcome decision tasks in which responses are made on continuous spatial scales. This is, of course, not a new idea. It goes back to the old method of adjustment of classical psychophysics, where researchers measured thresholds by asking people to adjust the intensity of a variable stimulus so it matched a standard stimulus. That method was given a modern makeover and reintroduced into modern cognitive psychology by Blake and colleagues and by Prince-Metal and colleagues in the 1990s. But probably the most influential paper was the paper by Patrick Wilkin and Wei-Ji Ma in 2004, who used it to study visual working memory. And there's now quite a cottage industry surrounding the use of this method in relation to this task. So this is a very typical application. It comes from Zhang and Lux's 2008 paper looking at visual working memory for colour. So the basic task, which is probably familiar to you, on each trial, you present a variable number of colour patches of differing hues in an isoluminate colour space, which the person needs to encode in memory. At the end of the retention interval, you probe a particular location and say, tell me about the colour of the patch at this location. And the person's task is to make some sort of manual movement or sometimes an eye movement to the corresponding point on the surrounding colour wheel, which matches the colour of their memory of the stimulus. And the typical data that you obtain from this task are peaked heavy-tailed distributions of response errors centered around the true color. So the size of the peak varies with the number of items in memory. More items gives lower peaks, and then you have these heavy tails that extend to the left and right. And there's been a very active debate for the best part of 2 decades now about whether the shape of these distributions is evidence for an item capacity limited memory store or not. I don't propose to go there. I don't propose to say anything about that debate. I'm not convinced that the question is completely well posed. But I became interested in this because I do some work in visual working memory, and I found myself increasingly criticised for using 2-choice tasks. So the claim was, why are you using these tasks? They provide less information. Indeed, I think the increasing use of continuous outcome tasks parallels the increasing use of response time distributions in decision research in general. And the motivation is the same, is to use tasks that give you richer data and may give you a better picture of the underlying process. So I was using 2-choice tasks because there was no decision model at the time, which would also predict response times. So in the face of these criticisms, I decided, well, I'd have to do it myself. So the result was the circular diffusion model, which was published in 2016, which represents the decision process as evidence accumulation on the interior of a disk, whose bounding circle of radius A represents the decision criterion for the task. So because this is a 2-dimensional process, the drift rate, which determines the rate at which evidence accumulates in the process, is vector valued. So it has a length or a norm and a direction or a polar angle. So the norm represents the quality of the encoded evidence, and the direction represents the identity of the encoded evidence. So the direction determines the rate at which evidence accumulates towards the boundary. The norm determines how rapidly that will happen. Now, apart from that, the model behaves pretty much like any other familiar diffusion process model. Evidence accumulation starts at the center of the disk and then meanders about diffusively until it hits a point on the bounding circle. So this irregular blue fractal-like trajectory represents the sample path or the accumulation trajectory of the process on a single experimental trial. So it hits a point on the boundary. The hitting point on the boundary represents the decision outcome, where the participant moves their mouse or their eyes, however you're asking them to make the response. And the hitting time determines the decision time component of response times. Now that model, although at first blush it looks fairly complicated, has lots of nice properties. It's very tractable analytically. We have nice expressions, nice comparatively simple expressions for all of the things that we're interested in, as I'll show you on the next slide. But one of the important properties is that it predicts von Mises distributions of decision outcomes. So the von Mises distribution is a circular analog of the normal distribution, but defined on a circular rather than a linear domain. And that's the fact that it predicts those kinds of distributions is important, because in the visual working memory literature, error distributions are typically modeled as mixtures of von Mises components. So the model explains why the von Mises distribution should arise. It claims it's an expression of evidence accumulation by an underlying diffusion process. So the three distributions in the panel on the left show three predicted distributions of decision outcomes for different values of the polar angle of the drift rate. The distributions are otherwise the same, but the center of the distribution moves. Now, the von Mises distribution is characterized also by a precision or a concentration parameter. So loosely, precision is the reciprocal of variance. High precision is low variance, and conversely. So the three distributions on the right are three predicted distributions of decision outcomes for different levels of precision, or that display different levels of precision: high, medium, and low precision. And another nice property of the model is that it gives a decomposition of the von Mises precision parameter into simpler cognitive components. So the von Mises precision parameter, often denoted kappa, in the model is predicted to equal the drift rate norm multiplied by the radius of the criterion circle divided by the diffusion coefficient. To put that in other terms, it's equal to the quality of the evidence in the stimulus multiplied by the amount of evidence that you use to make a decision, divided by the noisiness of the underlying process. Now, the model also predicts response times. Indeed, it predicts entire joint distributions of response times and decision outcomes. And I'll show you some examples later. So the joint distributions are obtained from a transformation of the distribution of a zero drift process via the Gersenov theorem, or if you want to be Russian about it, the Gersanov theorem, that we probably don't, or sometimes the Cameron-Martin-Gersanov theorem, but it's a change of measure theorem, or however you denote it. And what it says is that you can get the distribution of the process that you're interested in, which is the process with a non-zero drift, by multiplying the distribution for the zero drift process by this function ZTX. So the zero drift process is in fact a Bessel process, which is the Euclidean distance process of a zero drift process from the center of the circle. So if the process starts at the center of the circle, everything that you need to know about it is contained in the Euclidean distance from the center of the circle. And because the drift rate is zero, the outcomes will obviously be distributed uniformly around the circle. So the Gersenov theorem says that to get the joint distributions of outcomes and decision times, you multiply the distribution for the Bessel process by this function ZTX. So ZTX is technically an exponential martingale. A martingale is just a stochastic process with constant expectation. But ZTX has an illuminating form. It can be factorized into the product of two terms, one of which depends on the decision outcome, but is independent of the decision time, and the other of which depends on the decision time, but is independent of the decision outcome. So this term on the left-hand side is just the dot product of the drift rate vector, drift rate vector dotted with the coordinates of the point at which the process hits the criterion circle, that it exits the criterion circle. Now, it's an immediate consequence of this factorization that decision times will be independent of decision outcomes. In other words, response times will be the same in all directions. So the panel in the top right-hand corner shows selected distributions of decision times at different points around the criterion circle. And as you can see, that these distributions are all scaled copies of one another. If you condition on the area under the curve, they will all be identical to one another. So it's a consequence of this property that the basic model predicts that mean decision times will be the same in all directions. So the blue function in the bottom right-hand corner is the predicted mean decision time for particular values of criterion and drift rate. And as you can see, it's constant as a function of hitting angle, as I've called it here, or decision outcome. However, if you add in across-trial sources of variability to the model, it will give you continuous counterparts of the fast error and the slow error properties of the standard diffusion model. So variability in the radius of the criterion circle will give you fast errors. Variability in drift rate will give you slow errors. And that's the one that I'm going to concentrate on because it's the one which is relevant to the data that I'm going to talk about. And so you can see this slow error pattern in the red and the green functions in the lower right here. So these are the mean reaction times or mean decision times that you predict when you have trial-to-trial variability and drift rate. And the slow error pattern, the continuous slow error pattern, appears as a kind of dish-shaped function where the fastest responses are the most accurate ones with a hitting angle of 0 for the centered process, and responses become progressively slower as you move out towards the extremes. So the two functions I'm showing you here are just for different values of the drift rate variability. Now, the first application that we looked at of this model was looking at decisions about noisy color patches which were perturbed with chromatic noise. So this was a paper published with Sam Saba, Elaine Corbett, and Simon Lilburn. So the task, in the task, we presented participants with a single centrally located color patch in an isoluminant color space, which was perturbed by various levels of chromatic noise. The participant's task was to determine the dominant hue of the patch, the underlying hue of the patch, and to make a saccadic eye movement to the corresponding point on the surrounding color wheel, in this instance, somewhere in the teals. So this was an eye movement decision task, a kind of an analog to the widely used task with monkeys. And so we did this with a small N design with 4 practiced participants with varying levels of chromatic noise to vary the difficulty of the task. So this panel shows the marginal distributions of decision outcomes and decision times for the 4 participants for the 3 levels of noise. So the highest level of noise at the top, so the most difficult condition, the lowest level of noise at the bottom, the easiest condition. So the symmetrical distributions on the left-hand side are the distributions of decision outcomes. The skewed distributions are the distribution of decision times. And we modeled these data in the usual way with the usual assumptions that you would employ in using a diffusion process model, that decision criteria and non-decision times were constant across all levels of noise. And the only thing that varied with stimulus noise condition were the drift rate parameters. And by and large, the model is doing a pretty good job of picking up the structure in this data. The heavy-tailed distributions that you see at the top in the high noise condition that all participants displayed, we attributed it to an encoding failure process. So the idea is that at high levels of noise, rather than encoding the dominant color, the background color, participants encode some part of the noise, and the response is determined by that, which leads to a uniform distribution around the circle. Now, In the two-choice world, the interesting information, the important information in comparing models is typically contained in the relationship between the response time distributions for correct responses and errors. An analogous situation, I think, applies with continuous outcome tasks, where the interesting information is contained in the joint distributions of response time and decision outcomes, which I'm showing here in the form of a QQ plot, or a Q times Q plot, where on the x-axis, we're plotting quantiles of the distribution of decision outcomes, and on the y-axis, we're plotting quantiles of the distribution of decision times. And what you can see is that fairly consistently, participants are showing a distributional counterpart of the slow error properties, that the QQ plot has this kind of dish-shaped that we've associated previously with slow errors, which the model predicts successfully by a cross-trial variability in drift rate, primarily in drift rate in the radial component of drift rate, or in the drift rate norm. So in pretty much all of these participants, we see a slow error pattern, and the model is fairly successfully accounting for that as a function of drift rate variability. Now, early applications of continuous outcome tasks in areas like visual working memory assumed that the stimulus spaces were isotropic. That is, that they were the same in all directions, that the speed and accuracy of responses were the same regardless of where the stimulus was located in the stimulus space. Now, there's increasing evidence that that isn't the case, but rather that people are biased towards certain parts of the space. And that makes them faster and more accurate to stimuli located in those parts of the space, possibly in the direction of nameable colours. So we incorporated into the model a bias model, which is really a drift rate bias model. I won't show you the details now. We can look at that in question time if you like. But the basic idea is that biases are represented by vectors which are located in particular parts of the space, which combine with the drift rate vector to bias responding in either a clockwise or an anti-clockwise direction. So here in this plot, we're now plotting as a function not of the response, but of the stimulus angle. I'm sorry, the legends are very small here, but we're plotting as a function of stimulus angle. That is where the stimulus is located in the color wheel. And then on the left-hand side, on the y-axis, we're plotting the mean signed angular error. So positive angular errors mean that people tend to respond anti-clockwise to the true direction. Negative angular errors indicate that they're responding clockwise from the true direction. And there's a corresponding pattern in response times, because the model says if the stimulus vector aligns with one of the drift rate vectors, so the vectors are collinear, people will be faster and more accurate in that direction. Now, there are substantial individual differences here, but there is a tendency for performance for the mean angular error to oscillate somewhat as a function of the position in the stimulus space, and the model is able to pick that up. And there is a corresponding pattern of oscillation in the mean response times because of differences in the drift rate vectors. So the model is picking up at least a fair amount of the structure at the level of the bias model. Interestingly enough, Bay recently published an EEG decoding study where he decoded representations in visual working memory and concluded that the biases are in fact stimulus biases in the representations rather than response biases, which fits nicely with the way we're conceptualizing them there. Okay, well, that's the circular diffusion model. So let's now move on through the dimensions. So everything that I've talked about up until now carries over smoothly to higher dimensions. We can think about a family of diffusion process models in an n-dimensional space on the interior of a sphere of dimension n-1. So the two-choice diffusion model can be thought of as evidence accumulation in the space R1 on the interior of a zero sphere. So R1 is just the real line, which are the possible values that the diffusion process takes. A zero sphere is just a pair of isolated points. So the pair of criteria can be conceptualized as a zero sphere. The model that we've just talked about, the circular model, evidence accumulation takes place in R2, the Euclidean plane, on the interior of a one sphere, which is just a circle. And this can carry over, if you wish, to diffusion in R3, the three-dimensional Euclidean space in the interior of a two sphere, which is just a regular sphere. And in all cases, the response rule is exactly the same. It simply says you accumulate evidence until the Euclidean norm of the process reaches a decision criterion, then you stop. And the same mathematics applies. The Gersanov change of measure theorem applied to the distribution of a zero drift n-dimensional Bessel process will give you the joint distributions. Okay, well, why would you want to? Why would you be interested? Well, I have been thinking about the spherical model a lot lately. This is new work. It's finding its way into print. I hope it's finding its way into print at the moment. The particular application concerns the problem of bimodality. Now, Roger Radcliffe also studies continuous outcome decisions. He has a different kind of model, which is an infinite array of accumulators, and he looks at different kinds of tasks. But one of the tasks that he looked at is a brightness discrimination task where the stimuli are Gaussian luminance blobs presented in noise, in random pixel noise in a semicircular region of the kind you see here. And what he found is when the display contains pairs of blobs of similar brightness, then you find bimodal distributions of decision outcomes separated by an amount which depends on the spatial separation between the stimuli. And Roger made the claim that the circular diffusion model can't predict these sorts of patterns. Indeed, there's a stronger implication here that bimodality represents a qualitative test that falsifies the entire class of models. So naturally, I was interested to investigate this. So I used a somewhat different task, which was more compatible with the underlying geometrical structure of the model, which was a continuous outcome version of the random dot motion task. So Bay and Luck published a paper on this in 2019. This figure is from Bay and Luck's paper. So this is the standard random dot motion task where the decision maker is required to identify the direction of a coherent motion in a cloud of randomly moving dots. But Bay and Luck did a continuous outcome version of this in which the motion could be in any direction and the decision maker was required to indicate on a point on the circumference of the circle the perceived direction of motion. And what they found is that this task produces bimodal distributions. Actually, we knew about this before their paper, but they were the first to publish it. So the distributions down below show distributions of outcome for two different levels of difficulty, low and high coherence. And as you see, the task produces a single central peak, or a central peak centered on the true direction of motion, and a secondary peak, a secondary mode, or as I like to call it, a shadow mode at 180 degrees to the direction of motion. Now, this is interesting from a number of reasons. Obviously, it's interesting from a vision science point of view if you're interested in modeling motion mechanisms, because it implies that people can perceive the axis of motion, but on some trials, they misperceive the direction of motion along that axis. But it's also interesting from a decision process point of view, which was the approach that I took. And I thought that this provides a useful and interesting task, a test bed for studying bimodal distributions. So we carried out a couple of studies on this and we compared various diffusion models, a couple of versions of the circular model and a spherical generalization of it. And it turns out that one of the spherical models was our preferred model for reasons that I will explain as I go along. So in this model, it assumes that you accumulate evidence by a three-dimensional process on the interior of a sphere. So because this is a three-dimensional process, the drift rate, which describes the rate and direction of evidence accumulation, is also a three-element vector. So the basic idea is that you accumulate evidence until the process hits a point somewhere on the bounding sphere, and then you project down meridians of equal azimuth to find the point on the response circle that corresponds to the response, and that's the response that you give. Now, the mathematics of this process are very much the same as the mathematics of the circular model, except of course we're now working in spherical coordinates. So we need a couple of polar angles to keep track of the process, one which codes the azimuth direction in the response plane, and the other which codes the elevation. So there's a natural question then of what is the third dimension? What does it represent? What does it represent cognitively? There's a long and a short story of this, but my interpretation is that it's a measure of the participants' uncertainty about the encoded stimulus representation. So for a stimulus which is completely ambiguous, the drift rate vector will point along the vertical axis either towards the north or the south pole. Under those circumstances, the distribution of hitting points will be circularly symmetrical around the poles, and when you project down to the response plane, that will give you a uniform distribution of responses. But that nevertheless begs the question of why you would prefer a spherical model to a circular model. And the answer is ultimately empirical, that it turns out that it has better joint distribution properties, as I will try and convince you in the next couple of slides. You can't distinguish the models at the levels of the marginal distributions, but if you look at the more fine-grained structure in the joint distributions, then you find that they make different predictions, as I will show you. So we looked at two mechanisms that might conceivably give bimodality in this task. Both involve drift rate variability. One simply involves drift rate variability along the axis of motion. The other involves a mixture of drift rates where the means of the two components of drift rate have the opposite sign, so plus nu and minus nu here. And you might expect this kind of two-component drift rate model from some kind of opponent process motion model, like a motion energy model. Now, drift rate variability alone will give you a secondary mode if it's larger enough, because on a proportion of trials, the process will drift in the wrong direction at 180 degrees to the true motion direction, and that will give you a secondary mode. But in order to get a secondary mode that matches that in the data, you need fairly large drift rate variability. And as we'll see, that will predict a slow error pattern, which is larger than typically what's found in the data. The two-component drift rate model fares a little bit better because you don't need such large drift rate variance to capture the data. Nevertheless, it does better in a spherical model. So models with a two-component drift rate distribution typically predict joint distributions that have this kind of double bowed pattern where the slow error pattern reverses towards the extremes. So in the panel on the right here, the fastest responses are at the center. They have the most accurate responses, and responding gets slower as you move out from the center. But if you move out far enough, that pattern reverses and responding gets faster. And the reason for this is simply because of drift rate variability, you've got a proportion of processes which are drifting in the opposite direction to a point 180 degrees from the true direction, and those processes tend to finish fast. And those tend to finish fast. Now, both the circular and the spherical model will predict this kind of double bowing pattern, but the circular model is more flexible. The the spherical model is more flexible. The circular model predicts a very tight relationship between the magnitude of the bimodality and the double bowing, which is relaxed somewhat in the spherical model if the drift rate vector is elevated above the response circle. So here I'm showing 3 different distributions of decision outcomes. The blue distribution is when there is no drift rate variability and it doesn't produce bimodality. You get a unimodal distribution of decision outcomes. There are 2 distributions shown here with drift rate variability, the green function and the red function. The green function is when the drift rate vector is in the response plane, where you get a small amount of bimodality. The red function is where the drift rate vector is 1 radian, around 57 degrees above the response circle, which gives you larger bimodality. And then this is simply because there is a component of drift rate in the vertical direction, and some of the probability mass associated with the hitting points gets smeared around the circle, which tends to elevate the tails of the distribution. Now, the model, as I've described it, the spherical model with two components of drift rate variability, does a fairly good job of data. We have a total of 11 participants in 2 different studies, which had slightly different methods. I'm just going to show you 2 for the sake of compactness. Both of these participants show fairly large shadow modes. So the manipulation here is exposure duration. We had 4 stimulus exposure durations, 176, 352, 529 and 706 milliseconds. So in all of them, these participants show large secondary modes, which the model picks up nicely, and it also predicts the shape of the marginal distributions. The panels on the right-hand side show the joint distributions, the QQ plots, and as you can see, they produce, there is a hint, there is a small amount of this double bowing that I talked about, but it's not large, and the model is picking up double bowing of roughly the magnitude that you see in the data. To give you an idea of the difference, let me just contrast the spherical and the circular model for another participant. This participant has fairly small secondary modes by comparison. If you squinted your eyes, you might persuade yourself that it really wasn't there, but there is a small secondary mode. What you see here is that the spherical model and the circular model both predict both predict the marginal distributions of decision outcomes accurately. There is no difference in the performance of the model at the level, or the models at the level of the marginal distributions. Where the difference becomes apparent is in the joint distributions. So by and large, the spherical model is predicting the shape of the joint distributions fairly well, slightly over predicting the tail quantile in the most difficult condition, but it's not a big miss. Whereas in comparison, the circular diffusion model is predicting a larger slow error pattern than you see in the data, which gets progressively larger as the task gets more difficult. And I won't show you, we can look in question time, that the same bias model that we applied carries over to 3 dimensions. So one last application is then we can go over into even higher dimensions. We can look at in particular at evidence accumulation in the interior of a 3-sphere in a 4-dimensional evidence accumulation space. Now that's a hard process to visualize. The picture on the left-hand side shows a topologist's attempt to do that, which may contain information. It may be informative to a topologist, but it doesn't convey a lot of intuition for the rest of us. But nevertheless, the process itself is conceptually straightforward in terms of its underlying structure. It simply says that you accumulate evidence by a 4-dimensional process until the Euclidean norm of the process reaches a decision criterion. Now, of course, we need to work in hyperspherical four-dimensional coordinates where we have three polar angles to keep track of where the process is in the space. But otherwise, the mathematics that we've talked about before carries over quite straightforwardly. We obtain the joint distributions of this process by applying the Girsanov change of measure theorem to the distribution of a four-dimensional Bessel process. Now, again, why would you be interested in looking at a four-dimensional process? Well, we use this kind of model to model decisions in the double target deficit task. So the double target deficit is one of those deep fundamental findings in cognitive psychology. The finding that if you have a pair of target stimuli, both of which have to be detected, which are presented simultaneously, your performance is surprisingly worse than would be predicted by an independent detector model of any kind. So this was first reported by Moray in Audition in 1970. A visual version was reported by John Duncan in 1980, and Elaine Corbett and I did a version of it in 2017, basically using Duncan's paradigm. So in our version of Duncan's paradigm, there's a single target and a double target task, where the task involves detecting digit targets among letter distractors. So in the single target task, on target absent trials, there were 4 letter distractors in the display. And on target present trials, there was a single digit target with among 3 letter distractors. In the double target task, on target absent trials, there was a single digit target and 3 letter distractors. And on target present trials, there were a pair of digit targets among 2 letter distractors. Now, you can model accuracy in this kind of task perfectly satisfactorily with a multidimensional version of signal detection theory. Duncan indeed did this. We were interested in response times, and in this paper, we modeled it with a hyperspherical, that is a 4-dimensional diffusion model. So the 4 dimensions in the process were simply evidence for the presence or the absence of a digit target at each of the 4 locations in the display. So the model is really a generalization of an idea that I wrote about in the context of the circular model in 2019, which was the idea that you can get categorical responding from the circular diffusion model if you partition the response circle up with decision bounds into quadrants. So the panel on the right-hand side shows a possible model for the double target deficit in a 2-item display. And so the idea is that responses in each of the 4 quadrants of the circle are associated with a different decision outcome. So a response in quadrant 3 would be associated with 2 non-targets and 2 noise stimuli. A response in quadrant 2 would be associated with a non-target in location 1 and a target in location 2. And response in quadrant 4 would be the converse, a target in location 1 and a non-target in location 2. And a response in quadrant 1 would be associated with a double target response. This idea can be carried over fairly straightforwardly to a 4-dimensional process, which is what we did. So we partitioned the hypersphere, the response, the 3-dimensional hypersphere, with decision bounds into 16 regions, technically orthants, which represent all possible patterns of digits and letters in a 4-element display. So there are 16 possible combinations of letters here and digits here. And so the 16 possible outcomes of the process in the orthants of the hypersphere represent the 16 possible outcomes of the decision task, which simply then got mapped down using the appropriate response rule to the 2-choice form of the task. So the responses participants were made were just target present, target absent. And so we mapped the 16 orthants down to target present, target absent responses. Now, I don't want to say a lot about this, and just to give you a very brief sense of the flavour of it, I'm just going to show you the double target task. We have modelled the single target task, and what I'm showing you is the brute data and the best and the worst of the individual participants. So the data here are represented in the form of a quantile probability plot, where we plot quantiles of the response time distributions against the choice probabilities for correct responses and errors. So the points on the x-axis on the right-hand side are correct responses, the points on the x-axis on the left-hand side are errors, and the points on the y-axis are just the corresponding quantiles of the distributions of response times in those categories. And we've separated out double target responses, present responses, and target absent responses because of the extreme asymmetry of performance in the two conditions. I don't want to say a lot about this other than to point out that, that the model is doing a fairly reasonable job of picking up what is a very complex, an atypically complex pattern of data for a two-choice decision task. If you're used to looking at these kinds of diagrams, they're typically much simpler than this. So the model is picking up a lot of the complexity here, including a kind of double-bowed pattern. It's missing a little bit in the tails here, but it's picking up, for instance, a crossover pattern for this participant for whom accuracy becomes worse than chance in some conditions. So I don't necessarily think, I'm not necessarily claiming that this is decisive evidence for this kind of model. Indeed, Elaine Corbett and I in the 2017 paper looked at some more conventional diffusion processes or conventional diffusion models, one involving racing processes and the other involving a single coactive process where the drift rate was combined across the locations. And those models also did fairly well. All I'm saying there is that I think that this is increasing evidence for this kind of model, and it's an interesting demonstration of what can be done. So to conclude then, what I've done is shown that the diffusion model for two-choice decisions can generalize in a very natural way to continuous outcome decisions. And it gives you a tractable model which has many of the same properties as the two-choice diffusion model and which have been successful in that model in accounting for two-choice data. There's an important methodological point that I've stressed, that the important information for evaluating models is contained in the joint distributions as represented in the QQ plots. So this parallels the situation in two-choice decisions where the relationship between the distributions for correct responses and errors turns out to be critical data for comparing the performance of models. In the continuous outcome world, we're now looking at the entire joint distributions. I've shown that the circular model generalizes in a fairly natural and easy way to higher dimensions, and we've looked at 3- and 4-dimensional processes. And I've sketched some reasons for why you might want to do this. So there's a sort of larger philosophical claim, I guess, which is that the evidence process may contain more information than just the identity of the stimulus, than just the thing that you're asking the decision maker to respond to. Information about things like participants' uncertainty about the encoded stimulus, which may also relate to interesting things like subjective confidence. So just at the moment, this is still very much a greenfield area with lots of exciting things to discover. So I'll stop at that point. Thank you for your attention, and I'll throw it open to questions.
Thank you, Philip, for your presentation. It was great and interesting.
Thank you very much.
Okay, everyone, any questions?
Yes, Hassan.
Yeah. Thank you very much, Professor. I have a question about the practical use of these models. You introduced your model around 6 years ago, but since then, psychologists have not used this model in practice very much. What you think? What's the reason for this? Is there any practical issue?
Yeah.
Or
Look, I think one of the reasons is that it's a relatively complex model. You know, people are reluctant to implement complex models, and possibly that's slightly my fault, and I should be doing more to actually put usable code out there. If you look at the history of the Radcliffe diffusion model, which was published in 1978, and it was kind of cited. The sites sort of ticked along for several decades, but they really started to ratchet up when various people, various third parties put the model into more usable packages. And a number of people did that. Francis Dewlinks did that. There was the Wiki et al. HDM model. There was one by Joachim van der Kerkhove. And so, I think that people who have been prepared to do the work and to put the model into an end user friendly form have done a huge amount. So now the model is being, as in the two-choice model, is being hugely used in all kinds of applications, in lots of individual differences studies where people are looking at epilepsy and sleep deprivation and dyslexia and whatsoever. And, and I think a lot of that has been encouraged by the fact that there's just an off-the-shelf package which they can use. I haven't done that because that there's a lot of work associated in producing user-friendly code, which is bulletproof. What I've discovered as a scientific programmer over time is that you don't make programs any more complicated than you need, because the scientific question tends to change and code becomes rapidly obsolete. But from the point of view of end users, someone putting together a package which contains useful diagnostics, which can pick up, which gives a kind of a common interface and structure that someone can just say, okay, I can use this. This has been debugged. I think is one of the things that would lead to its uptake. But if you going back to your original question, if you just look at the time course, the time elapsing since I first published this in 2016, is a brief flash in scientific time compared to the time that the two-choice diffusion model's been around. But you're pricking my conscience and suggesting that I should actually try and get some grant money, hire a programmer, and put some useful code out there in the world.
Yes, thank you. I had another question. In one of your articles, you argued about the use of these models, for example, in the context of visual working memory. For example, in the Jiang and Locke's work in the article in 2008, they showed that the variance of the accuracy doesn't change between when we use, I think, 6 squares and 3 squares. But you argued that the precision and variance of accuracy is affected by 2 factors, the criteria and the drift. And it is very natural to think that the criteria, when the design of task is such that the difficulty is changed between blocks, the previous experience with using DDM and experimental data in such designs show that people may upper their criteria to get more accurate. And it seems so natural that this may happen here, and the not changing of the accuracy, variance in accuracy, may be the result of offering the criteria and lowering the drift rate, and as drift rate maybe represent the working memory capacity here. I thought that this was the natural next step in your works to check this, that if this is happening, and I thought that you may have tried this to see.
Yeah, so this is a source of great frustration for me. one of the reasons for developing this model initially was to take it into the visual working memory realm to look at precisely those sorts of tasks. My lab was shuttered in 2020, in March 2020, that we had done one version of the experiment and had to throw away the data because we didn't have a fast error trap. And so participants were actually responding prematurely, and we were seeing the leading edge of the RT distribution was being cut off. So in March 2020, we were about to do the visual working memory experiment, and my lab has been shuttered since then, and we haven't got back to normal data gathering. That's an aspiration. It looks as though we're gradually reverting to normal activity just at the moment, though my fingers, keeping my fingers crossed. I do have a couple of other applications of data sets that I had, which speak to your question as to whether behavior is best described by a mixture of a guessing-like process and a stimulus-driven process, or a continuously distributed single process. So one of those was, again, a version of the color task, which is where we varied exposure duration, and we got results very much like the 2020 paper. But another one was looking at an orientation discrimination task using Landolt rings. So these are rings with a small gap in them. And that looked as though it produced, and it was best fit by a two-component model. So a model in which you either had a single sharp stimulus-driven central peak or very flat tails where it looked as though people were responding essentially randomly. And my interpretation of that is that that's because Landolt rings, or the Landolt stimuli in general, is a hyperacuity task that relies on very high spatial frequency filters, which are slow to output. And so the interpretation is that on some trials, the filter outputs and you get a very accurate representation of the stimulus and the central peak is very sharp. But on others, it fails to output and you don't get a blurred representation, you get nothing at all. And so that gives you that sort of two-component, pattern. We're testing that at the moment. So the first experiment we've finally been able to start to run is a version of an orientation discrimination experiment where people report continuous orientation using arrowheads. So this is, again, a task which is used a bit in the literature, which is not a hyperacuity experiment, which is really a test of that hypothesis that the apparent two-component model that fits best is a reflection of the particular kind of visual stimuli. So that's the sort of long answer. I do remain a little bit skeptical about whether the question, the slot version of the two-component model, because the way this is represented, is described as working memory has a series of slots, and if the slots are full, then you have to guess. And I've never liked that because I've thought that it kind of reifies what's likely to be going on. I don't think that this is going to be an all or none thing, but rather that there is going to be some sort of energy cost, metabolic cost for coding more items. So rather than having a kind of discontinuity at your slot limit, there's probably going to be some sort of metabolic limit, and you're going to get graded responses rather than a sharp slot limit. And people continue to argue about this. There was the lovely paper by Kirsten Adam et al., which was a whole report task, which actually asked people to report on every item in the display in whatever order they found they preferred. And that looked like really strong evidence for a slot model. So people were accurate for the first 4 items, and then they were virtually at chance for the next 2. And so it really looked like a kind of hard item capacity limit. But Klaus Oberauer has just recently published a paper where he's attempted to replicate that, and he doesn't. So there's evidence that people still have some evidence out to 5 and 6 items. So yeah, that's just further reason for my sort of skepticism as to whether this is a really well-posed question. My strong sense is that yes, there are costs of encoding items, but it's probably not something quite as absolute as a hard item limit. So thank you. So Amin, if you've had your hand up patiently.
Thank you so much for your nice presentation. I have some quick question. First of all, as a modeler, I think that some models are much ahead of some basic concepts. And if, in your paradigm, I have a concern about what is really continuous decision making.
Mm-hmm.
Is it there is a real example to explain me why we think that there is a continuous choice? Because I think that for our working memory, we know that it is limited, and we can memorize each of option in the continuous options at the same time and think about each of option to make a decision. That is not consciously. I think when we want to choose the option between the continuous option, that is a little bit unconsciously.
So no, I'm having trouble getting the question. So are you concerned that the decision itself is not actually continuous, say in relation to the most concrete case of hue judgments, of color judgments, that's not really a continuous decision? Is that what you're suggesting?
I think that if we have continuous option, our brain just think about some discrete option, not all of option, and that is a little bit difficult.
So your proposition is that the cognitive representation is granular or discretized, is that right? And so that the continuous outcome is, in a sense, is an artifact of what really should be a discrete representation. Well, look, I think it's a reasonable claim. It's one of those things that you would need, you'd need to sort of chase empirically and try and provide some evidence. I think it's an empirical hypothesis. You would need to try and find evidence of this kind of granularity in data. I don't quite know what you would, how you would do that. The continuum is obviously is a very nice place to work. The continuum simplifies a great deal. One of the, if you're kind of familiar with the history of these models, one of the things that people have wrestled with is how to generalize the two-choice diffusion model to n choices, to a finite number of choices. Been a number of proposals, and there's nothing that has really been as elegant and as satisfying as the standard two-choice model, and nothing which has caught the attention of the field. So given that difficulty, it was really surprising, and it was really surprising to me how easily the model kind of carried over to the continuum, and how easily all of the mathematics carried over. So I think there are two things. One might like to work on the continuum for pragmatic reasons, because it simplifies life and gives you a nice tractable model, which is a purely pragmatic response, unless someone like yourself could come up with some compelling reasons which actually suggest that the underlying representation was discrete or granular. Some sort of information theory idea might lead you to that sort of representation. If we said you had a finite number of bits to represent things, and the finite number of bits would limit the resolution, and that should be expressed behaviorally in some sort of granular way. But I can't think of a better way of getting at that at the moment.
Thank you for your explanation. However, I think that one of the problems that psychologists couldn't be easy to use this kind of continuous decision making. I thought that in the real life, it's very difficult to make an example about the continuous and about the continuous decision. Another question is about the arrangement of color. I think in the classical decision making, we have some options, and the arrangement of that is not important. But in your paradigm, I think the arrangement of color is so important. For example, red comes after blue or not, because that change our decision.
But that's not arbitrary. That's a reflection of one dimension of an isoluminant color space. So if you take a color space and project it down, so you're only looking at one isoluminant slice of it. So you take the luminance component out, and so the arrangement of colors then falls out from the properties of the color space. So it's not arbitrary. It's a reflection of the physical properties of the color space.
Okay, but I think that that is arbitrary. What do you think that is the paradigm to select this arrangement?
So the decision task is arbitrary, you think?
No, about the arrangement of color. You think that is the paradigm to select how to arrange each of color in the circle?
But that's not a decision. That arrangement is not something that I made arbitrarily. That was simply taking a standard color space. It's actually one of the CIE 1976 spaces. It's the LUV space, which is their recommended space for luminance devices like monitors. So this is supposed to be a physical description of color space. Then the other one, which people often use, is the LAB space, which is supposed to be better for things like offset printers and print devices. So I guess my response is that I'm using a well-defined color space which specifies the arrangements of colors, and I'm simply taking an isoluminant slice through that, and there is no, I have no discretion as an experimenter. The space is the space, and the space is a given, so that's simply a reflection of the physical nature of color and the way color is represented mathematically, rather than something that I have done or I have chosen to do in this particular task.
Okay, thank you so much for your.
Amir, you've had your hand up patiently too.
First of all, thank you very much for your nice presentation. I have actually two questions. The first one is about the neural representation of the CDM, circular diffusion model. Could we imagine some sort of neural representation for the CDM or not?
Look, I think, that's a variant of the question. Can we envisage a neural representation for any diffusion model in a way? So I have done some work where, I've tried to derive diffusion process representations from quasi-neural stochastic processes, from Poisson shot noise processes that are supposed to describe how the flow of postsynaptic potentials arise as in response to a sequence of action potentials. And what I was really attempting to do was sort of clarify in my own mind as to why you would end up with diffusion, why diffusion at a sort of cognitive level is the right description for evidence accumulation, given what we know about the underlying neural processes. And different people have approached this in different ways. A number of people have just used diffusion approximations to mean field models. So I don't know whether you read this. So mean field models, models where you derive expressions for the overall firing rate of neurons in a population from assumptions about its dynamics, and typically they lead to attractor type models, which says that decision states are attractors in some sort of potential field. And so there have been a number of approaches which just say, well, we will derive firing rates and then we will simply assume a diffusion process approximation to that. I attempted to do that in a kind of bottom-up way, looking at the flux of postsynaptic potentials induced by action potentials, and derived diffusion representations from those sorts of assumptions. I personally found it a useful exercise to do because it kind of convinced me that cognitive level diffusion is a sensible and real thing. If you're looking for a linking hypothesis between what you're hypothesizing cognitively and what you think is happening neurally. And so at least in my mind, I kind of got a sense that you could get the diffusion process from this very simplified, but nevertheless kind of neurodynamic representation. So I haven't tried to do the exercise. I kind of think it should be possible to do for the circular diffusion model. But yeah, that's just a hypothesis. I haven't tried to do it, and I would attack it in the same sort of way. And there are other sets of assumptions that people make about continuous outcome tasks. I know Roger Ratcliffe is talking to you. I don't know whether he will talk to you about his spatially continuous diffusion model, which is closer in spirit to a kind of population code model, which basically suggests that you've got an entire distribution of stimulus strengths represented by firing rates in a population of neurons. And that idea has been picked up in the visual working memory literature by Wickstead and Brady, the Skirgen et al. Paper, which is again a population code model. So it's a sort of different set of assumptions. It basically says that you've got an entire distribution represented simultaneously, and the response is determined by the most active member of that population. So in a sense, it's a different set of assumptions. I guess my feeling is, the circular, as in the case of any scientific hypothesis, the circular diffusion model has some nice properties, despite being very, very constrained and restrictive. That's a question of seeing, just how far we can push it, whether it breaks and where it breaks. That's the way I would think about a neural representation, but I haven't done it yet.
Thank you for your complete answer. My second question is about adding some collapsing bond mechanism to the CDM, because in the context of continuous decisions, we have changing environment. And similar to the literature of the collapsing bonds in the discrete choices, the collapsing bonds have a better fitting when we have a changing difficulty in the task. So I think it could be nicely fitted to this context, and I want to know your opinion about adding some like this mechanism to CDM.
Okay, yeah, good question. The short answer is that I don't know how to do it analytically. I do know how to do it in the two-choice world. I don't know whether you've read my papers on integral equation methods. There was a recent one with Roger Ratcliffe, which and and I've been writing about those sorts of methods, which I think are sort of lovely and powerful methods for picking up all sorts of nice dynamics. Collapsing bounds is one of the dynamic things that you would want to put in. I think time varying drift rates is another thing that you might want to put in. Both of those seem to me to be eminently sensible things that you would want to put into a model. Sadly, in the CDM world, I don't know, to my knowledge, that there is no equivalent of the integral equation methods that will allow you to do the same thing for a circular model. From time to time, I've played with them, but it looks as though you kind of end up with potentially an infinite array of simultaneous equations, or something horrible and very difficult to work with. So I don't know. So it's certainly the case that with the CDM and with the various applications, including the spherical and hyperspherical versions, you're constrained to making the standard assumptions. Drift rate is constant during the trial. Diffusion is constant during the trial. You can always simulate it, of course. To me, I find simulation a kind of admission of defeat, but it's a way of getting a handle on more complex dynamics that you can't deal with analytically.
Thank you very much. Your papers always are very inspiring for me, and thank you for your presentation again.
Well, thank you. So there is a paper on the spherical model talking specifically about the issue of bimodality, which is under review. It's been submitted, reviewed, and resubmitted. So a lot of the issue that reviewers had was whether the third dimension is actually well motivated or not. I had a sense that it is potentially related to a number of things, which relates also to the collapsing bounds idea, which is the larger sense of urgency. So if you're reading the collapsing bound literature, you will know that a lot of this links into the idea that there is some sort of possibly neurally based urgency signal, which just impels you to respond. And it increases over time. And that's different to the idea of speed accuracy settings, of setting your criteria really low in order to respond. And, and I think that remains an interesting and ongoing area of debate as to, whether urgency really is a thing, and if it really is a thing, how it should be represented. And it occurs to me that the spherical model is another way of potentially thinking about urgency, because what it's basically saying, the larger premise behind this is that there is a decoupling in the quality of the evidence in the stimulus and the rate at which evidence accumulates. Now, that's not the case in the circular model, and it's not the case in the two-choice model. In both the circular and the two-choice model, if the evidence quality is low, then the drift rate is low, and you accumulate evidence really, really slowly. But there are various literatures. There's the urgency literature, and there is the overall intensity literature, which says that you tend to just respond faster to things that are more intense. So monkeys will respond faster to a choice between two equal high-value juice rewards than two low-value juice rewards. So it suggests that both of these literatures suggest that there's a kind of decoupling of the overall, I'm calling it the propensity or the tendency to respond from the information in the stimulus. An urgency is one manifestation of that. And one way of thinking about that in this kind of enriched framework is to think about it in terms of the spherical model, where the additional component is encoding your overall propensity to respond. So I'm trying to convince reviewers that that's a good idea. Mustafa.
Hello, Professor. Can you
Hello.
hear me?
I can, yep.
Okay. Thank you for your great presentation. I have a question. I would like to know, based on what we choose or mathematical space for modeling decision-making process. Can we think, you talk about other space, Euclidean space. Can we choose other mathematical space like Hilbert space and other space? I want to know about that. Based on what we choose this space?
Yeah, look, that's, I think, a deep and complex question, and I don't know that I have any kind of good or crisp theory about this. Psychology has tended, by and large, to work in comparatively simple spaces, Euclidean spaces, and so a lot of the theory of scaling, for instance, and multidimensional scaling has been developed in Euclidean space, and certainly in cognitive psychology, things like the context model and generalized context model use multidimensional scaling representations. I guess there are some non-metric forms of multidimensional scaling that have been developed by statisticians that have some applications in psychology, which have been less used in cognitive psychology. With regard to spaces like Hilbert spaces, which are infinite dimensional spaces, I guess I'm not certain. Hilbert space potentially provides ways of describing similarity and similarity of very complex functions, and that Hilbert space norms provide a way of describing closeness and distance in terms of more complex functions. I can't think of any immediate applications of that, and I don't know whether that will lead to nice, well-behaved models or very complicated models that give you a lot of grief. I can see reasons where, if you're talking about certain sorts of similarity structures, especially about complex functions, and there are maybe cognitive phenomena that might be represented in those terms, you might end up in a sort of complex high-dimensional metric space of that kind. Perhaps some of Tim Brady's work on similarity and long-term memory, and the fact that people are able to maintain very accurate long-term memory representations of very subtle differences between complex stimuli might lead you into a space of that sort, if you wanted to kind of characterize the similarity structure in a rigorous way. But beyond that, I don't know that I have any good suggestions.
Thank you.
Okay. Thank you, Philip. Thank you for presentation and answer the questions. It was our pleasure to meet you and have you in this mathematical psychology school.
Well, look, thank you again for inviting me. I think the school is a fabulous initiative and you have a really brilliant program. And it was really a great opportunity to meet you all. And, I hope to see you all thriving and flourishing in the cognitive and mathematical psychology world in future. I hope to hear more from all of you. So thank you.
Bye.
Bye.